It is assumed that when you view this video that you already know how to solve quadratic equations by factoring, by extracting roots, by completing the square, and by using the quadratic formula. The purpose of this lesson is to look at quadratic equations and to learn to determine what would be the most effective and efficient method for solving a quadratic equation. I'd like to begin by looking at how we define a quadratic equation. A quadratic equation is an equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a does not equal to 0. A represents the coefficient of the x squared term, b is the coefficient of the x term, and c is the constant. We refer to ax squared as the quadratic term. We call bx the linear term, and we call c the constant. Of course, if a were equal to 0, this would mean 0 times x squared, and 0 times x squared would be 0, which would mean that we wouldn't have an x squared term. A quadratic equation must have the x squared term. It may also have the linear term and the constant term. Now I'd like for us to look at the extraction of roots theorem and then the quadratic formula. The extraction of roots theorem says if x squared equals p, and notice p is any real number, p is a constant, then x is equal to plus or minus the square root of p. So the solutions for this equation would be equal to plus or minus the square root of p. For a quadratic equation, we write it in the form ax squared plus bx plus c equals 0. And do you remember what we call this form? That's called standard form, isn't it? We usually write a quadratic equation in standard form. Sometimes we say that we are setting the equation equal to 0. We may always use the quadratic formula to find the solution of a quadratic equation. We know that our solutions equal minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Remember that a in this case means the coefficient of the x squared term, b means the coefficient of the x term, and c refers to the constant when the equation is written in standard form. Now we've learned that the discriminant is equal to the b squared minus 4ac, that part under the radical. We may use the discriminant to characterize the types of solutions for a quadratic equation, but also we know that if the discriminant is a positive perfect square, then the quadratic is factorable. So if we're ever wondering whether a quadratic factors, we can figure out what its discriminant is to determine if it factors. Now I'd like for us to look at some different quadratic equations, and let's talk about what would be the best method for solving them. You might want to write the form down and the method that we will use. For this first form, I have ax squared plus c equals 0. Now notice that I have the quadratic term, I am missing the linear term, and I have the constant term. When I am missing the linear term, when I write the quadratic equation in standard form and I have the squared term and the constant, I choose to extract roots. Of course, a does not equal to 0 and c does not equal to 0, and that just means that we have to have the quadratic term and the constant, and in this case we're missing the linear term when we extract roots. For this second form, ax squared plus bx equals 0, notice that I have my quadratic term and my linear term. Which term am I missing? I'm missing my constant. Of course, a does not equal to 0 and b does not equal to 0 just means that I need to have the quadratic term and the linear term. When I am missing the constant, look at these first two terms. They have a common factor, don't they? They have a common factor of x. So I may solve an equation in this form by factoring. I factor out the common factor x. For this last form that I have here, notice I have mx plus n in parentheses squared equals p. M does not equal to 0. That just means that I have to have this term mx. Notice that this mx term is a linear term. This means x to the first power. M simply stands for the coefficient of x. N represents a constant. P represents a constant. When I have a quadratic equation and I have a binomial squared where the first term is a linear term, the second term is a constant, and I have a constant on the other side of the equation, once again I choose to extract roots. Now looking at two more forms, this is probably the most common form that we see, ax squared plus bx plus c equals 0, where I have all three terms, my quadratic, my linear, and my constant term. When I have all three terms, and of course saying a does not equal to 0, b does not equal to 0, and c does not equal to 0 just means that when I have all three terms, I factor if the quadratic will factor, or I may choose to use the quadratic formula. If it will not factor, or if I think it's going to take me too much time to figure out how it does factor. Last, I have a form that I would consider using the method of completing the square on. And notice this form. For my x squared term, the coefficient is 1. I have 1x squared plus bx plus c equals 0. If I have all three of these terms, and the coefficient of x squared is 1, and the coefficient of x is even, I would consider completing the square. In general, I do not solve by completing the square because very often it is just too involved. I think that it's easier just to go ahead and use the quadratic formula. But an equation that is in this form is not too difficult to complete the square on. Hopefully all of these methods for solving a quadratic equation are familiar to you, and now we'll begin solving some equations. Let's look at problem number 1. I am to solve. Of course, I know that when it says to solve, that means that I want to find the value for x that I can replace each x with so that this equation is a true sentence. I notice right off that it is quadratic, so I know that I want to try to write it in standard form. Of course, I need to remove the parentheses, so that's what I will do first. I need to distribute the x. X times x gives me x squared. X times 3 gives me 3x. Since it's quadratic, to write it in standard form, I want to set it equal to 0. I'm going to choose to move the x squared and the 3x. I move the x squared by subtracting x squared from both sides of the equation, and of course I line it up under its like term because we know we can only add and subtract like terms. Likewise, I need to subtract the 3x from both sides of the equation. 6x squared subtract x squared gives me 5x squared. Minus 16x subtract 3x gives me a minus 19x. And then I have minus 4 equals x squared subtract x squared is 0x squared. 3x subtract 3x gives me 0 on the right side of the equation. Now notice what I have here. I have all three terms, don't I? My square term, my linear term, and my constant. So my choice here would be to try to factor, and if I think it doesn't factor, it's too difficult to factor, then I want to use the quadratic formula. I would not consider completing the square because notice my coefficient of my x squared is 5. It's not a 1, and the coefficient of x is not an even number. So let's see if this factors on the 5x squared. Let's try 5x times x. On the 4, let's use a positive 1 and a minus 4. Let's check it. 5x squared minus 20x plus 1x gives me minus 19x. 1 times negative 4 gives me a negative 4. Now let's use our zero principle that says if 5x plus 1 times x minus 4 equals 0, that either 5x plus 1 equals 0 or x minus 4 equals 0. And let's solve each of these equations. I'll subtract 1 from both sides. I'll divide by 5. I'll add 4 to both sides. So I get my two solutions are negative 1/5 and 4. And I will write those using solution set notation. Of course, I can check both of these, but I will leave the check to you. For problem number 2, we are to solve. I chose this problem because notoriously my students think this problem is very difficult because it has the fraction. It may not immediately look like a quadratic equation even to you, but what's important here is that since I have the fraction, I need to get rid of the fraction. And after I get rid of the fraction, then I need to get rid of the parentheses, and then I will concern myself with whether it's quadratic or not. To get rid of the 2 in the denominator, I find, of course, that the LCD in this case is 2. So I multiply both sides of the equation by 2. So I'll have 2 times 14 equals 2 times 1/2 times x times 2x plus 1. On the left, 2 times 14 gives us 28. On the right, I have 4 things to multiply. I have a factor of 2 times 1/2 times x times a binomial factor of 2x plus 1. Of course, when I multiply more than 2 factors, I multiply 2 at a time, get the answer, and then I multiply it by the next factor. So I'll start with 2 times 1/2. Of course, 2 times 1/2, the 2's divide to 1. I'm simply left with 1 over 1, which is 1 times x. So 1 times x is x, and now let's multiply the x times 2x. We'll get 2x squared, and x times 1 is 1x. Now I can see that it's quadratic because it has the x squared term. I think it would be easier to put the 0 on the left this time, so I'm going to subtract the 28 from both sides of the equation, and I'll just write the 28 out to the side since it is not like the x squared or the x. I'll have 0 equals 2x squared plus x minus 28. Now once again, notice I have three terms in this quadratic. I have the square term, the linear term, and I have the constant. I will choose to try to factor it. If it doesn't factor, I will use the quadratic formula on it. I would not choose to complete the square because once again the coefficient of x squared is a number other than 1, and the coefficient of x is 1, which is not an even number. So let's see, 2x squared, let's use 2x times x. On the negative 28, let's use a negative 7 and a positive 4. Let's check. 2x times x is 2x squared. I'll get 8x, subtract 7x is positive 1x, and negative 7 times 4 is negative 28. I may now use my zero principle that says that if I have a product equal to 0, that one of my factors must equal to 0. So let's set 2x minus 7 equal to 0 and x plus 4 equals 0. Let's add 7 to both sides. We get 2x equals 7. Let's divide by 2. We get x equals 7/2. Let's subtract 4 from both sides. We get x equals negative 4. So our equivalent equations would be x equals 7/2, x equals negative 4. And so our solutions would be 7/2 and negative 4. Once again, I'll leave the check to you. As a matter of fact, I'll leave all the checks in this lesson to you. One thing I'd like to make a point here. If you look at this and you have trouble factoring it, if you want to determine if it factors or not, figure out what the discriminant is. Let's calculate the discriminant here. The discriminant is, remember, b squared minus 4ac. For this problem, our a is 2, our b is 1, our c is negative 28. Let's calculate and see what number this is. B squared would be 1 squared minus 4 times a is 2 times c is negative 28. So I get 1 minus 4 times 2 is 8, and 8 times the negative 28 would be a negative 224. So I have 1, of course, subtract a negative is the same as adding 224. So I get 225. 225 is a positive perfect square number. Remember, when the discriminant is equal to a positive perfect square number, that tells us that the quadratic is factorable. Now, actually, quite honestly, usually if I go to the trouble to figure out what the discriminant is, I don't go back and try to factor it. I just go ahead and use the quadratic formula. But I think we need to be aware that this does tell us whether a quadratic factors or not. All right, I also chose problem number 3 because notoriously my students have trouble with this problem also. We are to solve. It is obviously a quadratic equation. We have the quadratic term and the equals. Since it is quadratic, that should say to us to write it in standard form, because we solve most quadratic equations by writing them in standard form, which means that we need to move one of these terms. I'll choose to move the 4x. I'll move that 4x by subtracting 4x from both sides. Now, of course, on the left side, I only have an x squared term, so I'll write the minus 4x in its own column. So I have x squared subtract 4x equals 0. Now I want you to notice the form here. I have my quadratic term and my linear term. I'm missing my constant term. When I am missing either the linear term or the constant term, we call this an incomplete quadratic. An incomplete quadratic. For an incomplete quadratic that is missing the constant term, we may factor. We may factor because look at these two terms. What factor do they have in common? They have a common factor of x. So we factor the x out. In the first term we're left with x. In the second term we're left with minus 4 equals 0. Let's use the zero product theorem. Let's set each factor equal to 0. And of course, x equals 0 represents the solution of 0. And for our second equation, we'll add 4 to both sides, and we get x equals 4. So our solution set would be 0, 4. Problem number 4 says solve. Notice what I have. I have 2x minus 3 squared plus 12 equals 4. This is one of the few types of quadratic equations that I would not write in standard form. I would extract roots. Notice what I have here. I have a binomial squared. My first term is a linear x term. My second term is a constant. And the other numbers outside of my binomial squared term, my other numbers do not contain variables. They are constants. When these other numbers are constants, and I have this binomial squared, I isolate the binomial squared. I get the binomial squared by itself. Now, I hope that you're thinking, well, no, there's not an x squared term here, but certainly if I squared this out, when I say 2x times 2x, I get 4x squared, so it is quadratic. If I squared it out, I would have that quadratic term. But like I said, I do not want to do that in this case because I think there's a quicker way of solving this quadratic equation. So I'm going to get the 2x minus 3 squared by itself on the left side. That means I need to move the 12. I move the 12 by subtracting 12 from both sides. I'll have 2x minus 3 squared equals minus 8. At this point, when I have this quantity squared equals a constant, I will use my extraction of roots theorem that says that on the left I get 2x minus 3, and on the right I have plus or minus the square root of negative 8. Now I need to solve for x, but before I do, I'm going to simplify the square root of negative 8. I'll have 2x minus 3 equals plus or minus. I'll think of this square root of negative 8 as the square root of negative 4 times the square root of 2. The square root of negative 4 is 2i. And then I'll have my square root of 2. Remember, this means 2 times I times the square root of 2. Solving for x, I want to add 3 to both sides. Now I'm just sort of going to stick this 3 under here. Remember, this 3 is not like 2i times the square root of 2, so it has to have its own column. So I'll have 2x equals 3 plus or minus 2i times the square root of 2. And last, I want to divide both sides of the equation by 2. So I get x equals 3 plus or minus 2i times the square root of 2 all over 2. Using solution set notation, I may write this or remember, this actually represents 2 solutions, so I could write 3 plus 2i times the square root of 2 over 2, and the other solution is 3 minus 2i times the square root of 2 all over 2. For problem number 5, I obviously have a quadratic equation. It's already written in standard form, isn't it? But notice I only have 2 terms on the left. I have the quadratic term and the constant term. Which term am I missing? I'm missing the linear term. This is also called an incomplete quadratic. Now, this time when I am missing the linear term, I am going to extract roots. What I need to do is to isolate the x squared term. I need to solve for x squared, and then I will use my extraction of roots theorem. So, to isolate the x squared, let's add 7 to both sides. We have 5x squared equals 7. Let's divide by 5. We get x squared equals 7/5. Let's use our extraction of roots theorem, which says that x equals plus or minus the square root of 7/5. Now, we are not going to leave this fraction under the radical. We need to simplify. Let's multiply by 5 over 5. So we'll have plus or minus. In the numerator, we'll have the square root of 35. In the denominator, we'll have the square root of 25. So that will simplify as plus or minus the square root of 35 over 5. So let's write that as a solution set. And of course, if we would like to write those solutions individually, we may write the square root of 35 over 5 and minus the square root of 35 over 5. I would like just to review once again. Notice what led me to solve for x squared and to extract roots. It's the fact that I do not have a linear term. I think this is the quickest way to solve a quadratic equation that is missing the linear term. Now, let's look at problem number 6 we are to solve. Well, before we determine whether it's quadratic or not, we know we've got to remove the parentheses. So we'll remove the parentheses first, and then we'll be able to tell it's quadratic. On the left, I have a binomial times a binomial, so let's FOIL. Let's say 8x times 2x is 16x squared. For an outer product, 8x times 3 gives us 24x. For an inner product, negative 5 times 2x gives us negative 10x. So 24x subtract 10x will give us a positive 14x. And negative 5 times 3 will give us negative 15. On the other side of the equation, let's distribute the 2. 2 times 3x is 6x. 2 times negative 5 is negative 10. It's very obviously quadratic, isn't it? It has the quadratic term. Let's write it in standard form. Let's subtract the 6x from both sides. Let's add the 10 to both sides. So we get 16x squared. 14x subtract 6x gives us a positive 8x. Minus 15 plus 10 gives us a negative 5 equals, and on the other side we get 0. Now, we could take some time and try to figure out if it factors or not. We could figure out what the discriminant is, and if the discriminant is a positive perfect square, then we would know it would factor, but I think I'm just going to go ahead and use the quadratic formula on it. Since it is written in standard form, and remember it has to be written in standard form to use the formula, we write it in standard form before we decide what A, B, and C are. Our A, which is the coefficient of the x squared term, would be 16. Our B is the coefficient of the x term. It is 8. Our C is the constant. It is negative 5. Our formula says that x equals the negative of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So let's substitute our a, b, and c into the formula. So our x will equal minus 8 plus or minus the square root of 8 squared minus 4 times our a, which is 16, times our c, which is negative 5, all over 2 times our a, which would be 2 times 16. So we have negative 8 plus or minus. Now remember, when we simplify what's under the radical, we first square the 8, and then we want to figure out what 4 times 16 times a negative 5 is. Let's hold this minus right now. 4 times 16 is 64. 64 times a negative 5 would give us a negative 320. We'll subtract a negative 320 would give us a positive 320, wouldn't it? All over 2 times 16 is 32. So we will have a negative 8 plus or minus. Now we need to add these two numbers together before we try to simplify this square root. We'll have 64 plus 320, which would be 384, all over 32. Now some teachers would let you give decimal values here, and if you are allowed to give decimal values, then you may calculate. Remember to say minus 8 plus the square root of 384 and divide all that by 32, and minus 8 minus the square root of 384 and divide all that by 32. The first value would be approximately equal to 362 thousandths. The second value, minus 8, subtract the square root of 384 over 32, is approximately equal to minus 862 thousandths. These are approximate values because I've had to round. Some teachers will take them, some teachers will not. Some teachers want the exact values, and if your teacher wants the exact value, then this represents the exact value, but we always want that exact value simplified as much as possible. So what we want to do is to work on this square root of 384. Of course, we want to figure out what perfect square, what's the largest perfect square that's a factor of 384. Some of my students are really good at that and some of them really aren't. If you're not really good at it, I suggest to you that you take this number 384 and write it as factors of its primes. Find the prime factorization. So I'm going to do that because a lot of my students really have trouble with this. You can start, 4 goes into this evenly, but 2 does. So let's just start with 2. 2 divides into 384 192 times. So 2 is one of the prime factors. On the 192, I know that 2 is a factor of 192, so I'm going to use 2 again. 2 times 96, and so I've got another prime factor. On the 96, let's use 4 times 24. Neither one of those is prime, but we can factor the 4 into 2 times 2, so that's prime. On the 24, let's use 3 times 8. The 3's prime. On the 8, let's use 2 times 4. The 2's prime. And on the 4, 2 times 2. So let's see what we've got here. How many of these 2's do we have? 1, 2, 3, 4, 5, 6, 7. So that would be 2 to the 7th times 3, and if you want to check, figure out what 2 to the 7th is and multiply it times 3, and it should give us 384. Well, of course, we know we're looking for perfect squares, and we know that perfect squares are even powers, so we want to break this 2 to the 7th up as 2 to the 6th times 2 times 3. So if we want to simplify the square root of 384, what is 2 to the 6th? Do you know? We could write this as the square root of 2 to the 6th times the square root of the 2 times 3 is 6, and the square root of 2 to the 6th is 2 to the, remember, take this power 6 and divide it by the order 2. 6 divided by 2 would be 3, times the square root of 6, and 2 cubed is 8. So 8 times the square root of 6 represents the simplification of the square root of 384. Of course, some of you would prefer to think that it's the square root of 64 times the square root of 6, and of course the square root of 64 is 8 times the square root of 6. But I know that a lot of you have a lot of difficulty with this, and sometimes my students seem to have more success with this prime factorization method. Whichever way you work this, we know that the square root of 384 then is 8 times the square root of 6. So let's go back to our problem, and in place of this square root of 384, let's write 8 times the square root of 6. So we have simplified the radical. Now we need to see if we can reduce the fraction. Remember that the minus 8 and the plus or minus 8 times the square root of 6, this represents separate terms. So if we're trying to reduce, we need to look for a common factor in this term, and in the denominator. And sure enough, they have a common factor of 8. So I'm going to factor the 8 out. In the first term, if I factor 8 out of a negative 8, I'll have negative 1. Plus or minus, when I factor an 8 out of 8 times the square root of 6, I have the square root of 6 all over 32. And since the 8 is a factor of the numerator and the 32 is understood to be the only term in the denominator, I may say 8 goes into 8 once and into 32 4 times. So simplified, I get minus 1 plus or minus the square root of 6 for the numerator all over the denominator of 4. And if you calculate this minus 1 plus the square root of 6 and divide that by 4, and minus 1 minus the square root of 6 divided by 4, you should get these very same two numbers. So if your teacher asks you for the exact solution, then you want minus 1 plus or minus the square root of 6 over 4. And if you are allowed to give rounded solutions, we would have 362 thousandths and minus 862 thousandths. Now I would like for us to look at one last problem. It is obviously quadratic. Let's write it in standard form. That means I want to move the 8x over, and I will subtract the 8x from both sides. And of course, on the left, since I don't have an x term, I saved a space. So I'll have x squared minus 8x minus 2 equals 0. Now, in this case, I have 3 terms, don't I? Since I have these 3 terms, I may choose to factor. If it factors, I may use the quadratic formula, or I could complete the square. Now, this one does not factor, and I probably would choose to use the quadratic formula on it, but this one is not too difficult to complete the square on, because the coefficient of x squared is 1. And notice what the coefficient of x is. The coefficient of x is negative 8, and negative 8 is an even number. So let's complete the square on this. Remember, when we complete the square, first thing is make sure that the coefficient of x squared is 1, and it is. Next, we move the constant over by adding 2. We get x squared minus 8x equals 2. Now remember, what we want to do is to add a number to x squared minus 8x so that the resulting expression is a perfect square trinomial, which we know factors as a binomial square. The way we figure out what number to add is we take the coefficient of x, we divide it by 2. That gives us negative 4. We take that negative 4 and we square it. That gives us positive 16. So that tells us that we're going to add 16, and of course we have to add it to both sides of the equation. On the left, our x squared minus 8x plus 16 is a perfect square trinomial. It factors into x minus 4 squared. On the right, we simply combine our numbers. 2 plus 16 is 18. Next, since our equation is in the form of a binomial squared and we have a constant on the other side, we'll use our extraction of roots theorem, which says that on the left we have x minus 4, and on the right we'll have plus or minus the square root of 18. Let's simplify the square root of 18 and let's solve for x. I think of the square root of 18 as the square root of 9 times the square root of 2. The square root of 9 is 3. So I'll have 3 times the square root of 2. Solving for x, I want to add the 4 to both sides of the equation. And remember that the 4 is not like the 3 times the square root of 2, so it needs its own column. We get x equals 4 plus or minus 3 times the square root of 2. So my solution set here would be 4 plus or minus 3 times the square root of 2. That wasn't too difficult, was it? I would suggest that you only use completing the square when you have a quadratic that has the squared term, the linear term, and the constant. The coefficient of the squared term is 1, and the coefficient of x is an even number. I hope now that you have some feel for being able to look at a quadratic equation and determine the quickest way and the easiest way to solve it. This completes the Solving Quadratic Equations summary. Please rewind the tape before you return it. Thank you.